All right, here comes 12.2 independent and dependent events. Independent events are when one event does not affect the occurrence of another event. So, examples: rolling dice and then flipping a coin. Notice they don't really affect each other. You're just going to do one event and then the other event. Choosing a marble from a jar and then picking a card. Rolling a dice and then answering a true-false question. Okay, those are all independent events. They don't really affect each other. Dependent events, when a one effect does affect the occurrence of another event. And usually what you'll see is that it's going to involve replacement, and it's usually going to be without replacement. Not with replacement is going to infer that nothing changed, so it'll be a independent event. But when it's a dependent event, it's going to be without replacement. So when you pick up a card from a deck, then you pick up another card before replacing the first one. That's probably the most common one you'll run into. Flipping a coin in order to decide which answer is true or false. I don't really like that one, but it's true. Like, if you're going to choose true or false, it depends on what, side of the coin you flipped. But this is the all-star one, that first one, picking a card out of the deck and then picking another one and not replacing it without replacement. So that's going to be dependent events that we're running into. Here's some examples. Determine whether these are independent or dependent events. A student taking a quiz randomly guesses the answer to 2 true or false questions. If you answer the first one true or false, and then you answer the second one true or false, you didn't really base anything off each other. They're both independent of each other. Independent. A group of 4 students includes 1 boy and 3 girls. The teacher randomly selects one of the students to be the speaker and a different student to be the recorder. Well, if you choose one person to be a speaker, right, and then a different student to be a recorder, you are picking from 4 kids the first time, and then now you're only picking from 3 kids the second time, because they can't be both a speaker and the recorder. So your second event depends on that first event. So this would be a dependent. A bag contains 6 pieces of paper, numbered 1 through 6. A student randomly selects a piece of paper, replaces it, and randomly selects another piece of paper. If you so you choose 1 of 6, right? Let's just say you choose 1, but you put the 1 back into the bag, right? So you had a 1 of 6 chance grabbing a 1. Okay, now you're going to put that back. You have still a 1 of 6 chance to pick any of the other ones, right? So these are actually this is independent. If it was without replacement, you just change it to a 1/5 chance, right? Not a 1/6 chance anymore. So without replacement will be a dependent. That's the game changer there. All right. Finding probability of independent events. Probability of A and B happening is going to be the probability of A times the probability of B. Find the probability of 2 independent events. As part of the board game, you need to spin a spinner, which is divided into equal parts. Find the probability. You'll get a 5 on the first spin, and the number greater than 3 on the second spin. So first off, you have 8 things you could spin on, right? So let's write the probability of A is 1 of 8, because there's 8 dials you can spin on. 1 divided by 8. Okay. A number greater than 3 on the second one. So this is going to be the probability of B equals what? Well, we have 1, 2, 3, 4, 5 that are greater than 3. If it said greater than equal to, we include 3. So there's only 5. So 5 of 8 on the second one, because they're both independent events. So that 8 doesn't really change. All right. So the probability of A and B is going to equal 1 over 8 times, let's see, 5 over 8. Wow, I ran out of room very quickly here. I got 5 over 64. Oh, wow, that's a bad 5. There we go. 5 over 64. Should get 0.078. So that'll be 7.8%. Let's see if I can thin this out here. But yeah, you know how this kind of functions. Oh, there you go. Great. If you want to change a decimal to percent, you move the decimal place over twice, and then it becomes the percentage. So 7.8%. Cool. That's probability that you spin an even number and then an odd number. Okay, so probability of A is the even number. 1, 2, 3, 4. Right? If you didn't want to count, you probably realize that there are 4 even numbers in 1 through 8. Some people can pick. If you're kind of good with numbers or good with whatever type of thing that's kind of happening, whether it's a spinner, whether it's cards, whether it's dice, some people are better at just understanding what the context is better. So they can just kind of come up with these numbers too. How many odd numbers do we have? 1, 2, 3, 4, right? So it's 4/8 again for probability of B. All right, same thing. Probability of A and B equals. And notice these are both 1/2, so you can really just do 1/2 times 1/2. If you want to do 4/8 times 4/8, you'll just have to simplify it later. This will get you 0.25 either way you slice it, which is 25%. Cool. All right, moving on. Finding probability of dependent events. So this one's a little different. Okay, I left this here from Cranby. Okay, it's the probability of B. Sorry, probability of A and B for a dependent event is going to be the probability of A times this. And sorry, that slash right here really should be going vertical, but we don't have really a thing to type in the computer. So it really should be like this. Okay. And what that means is it's the probability of A given. That's what that line represents. Given that A has happened. So it's kind of like a reverse. Probability of B given A has happened. Okay. So let's kind of see what that looks like. Find the probability of 2 dependent events. A bag contains 20 $1 bills. That's important. If you're not great with word problems, you probably underline. That's what I like to do. Important details. 20 $1 bills and 5 $100 bills. You randomly draw a bill from the bag, set it aside. Oh, that's important. Setting it aside without replacing it, right? and then randomly draw another bill from the bag. Find the probability both events A and B will occur, given the situations. Here's A. Find the probability that the first. Find the probability that the first bill is a 20. Is 100, and the second bill is also 100. All right. Well, you know that there are 25 bills total. That's going to be important, right? 20 and 5. So 25 bills. Okay. How many bills, right, is the first occurrence going to happen? Probability of A. What's going to be that? Well, if there's only 5 bills that are 100, you have a 5 of 25 chance that the first one's going to be a $100 bill. Now you set the 100 bill to the side, right? How many bills do you have left? You have now 24 bills left. Now you're going to pick again, but now you don't only just have 24 total bills left in the bag. You have one less $100 bills, right? You went from 5 $100 bills to 4 $100 bills because you set the first one aside. So the probability of B given A just happened, you pulled the $100, is that you have 4 $100 bills out of 24 total bills left in the bag. Okay, these are the ones that you have to pay attention to the wording on. Okay, so now let's clean it up. Probability of A and B. B. There we go. Equals 5 over 25. If you wanted to simplify it, that's fine. Sometimes it's just easier just to not. Times 4 over 24. This is what I would do in the calculator. 5 over 25 in parentheses times 4 over 24 parentheses. It's probably the easiest way. That way you don't mess up the rounding. Should get 0.03 repeating. So then you just round it up, or not round it up, but change it to a percentage, and you get 3.33% of that event occurring. Cool. Find the probability that both bills are $1 bills. All right, you should probably try this on your own, right? Just mimic kind of what we just did. But the first part, you choose a $1 bill, one of the $20 $21 bills. So there are $21 bills, so 20 out of how many bills are the total? 25. Now you take out one of the bills, right? You set it aside. B given A, right? So we just said that. So now you have only 19 $1 bills left, and you have only 24 bills total left because you set that $1 bill in the first event aside. Okay, so now we multiply these. I'm just going to write the multiplication because we did that same thing up here. That's not what I wanted. Pop. 20 over 25 times, I'll do that, times 19 over 24. Cool. And I got, should be higher, right? Should get 63.3%. I skipped moving the decimal place step just to the percentage. Alrighty. Oh yeah, card time. Some people really like cards. This is where probability comes into play. Comparing independent versus dependent events. You randomly select 3 cards from a standard deck of 52 playing cards. So if you don't know about cards, here's a couple things. 1, you have 52 cards total that you don't include the jokers with. People don't ever play with jokers, so we don't count them. Some people do, I understand, but usually you don't. So 52 cards total. A fourth of the cards are in suits. You have jacks. You have spades, which is the one I'm pointing at right there. Spades, clubs, which is up here. Clubs. Okay, and then obviously diamonds and hearts. Those are the four different suits. That's what you call suits. Suits. Okay, and they're a fourth of the deck, right? A fourth of 52 is going to be 13. There's 13 of these cards. You can count them too, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And that's for each suit. So 13 of 52, you simplify that, that's the same thing as 1/4. So that's that's pretty important to know, right? Especially when we're going to talk about cards in a moment here. All right, there's probably more to say, but we'll just leave it there. What is the probability? What is the probability that all three cards are hearts when you replace each card before selecting the next card? Okay, so we're going to put it right back in the deck, right, with replacement. So you have a 13 of 52 chance that you draw a heart. You put it back in the deck, right? Well, you still have that card's still an option. So it's 13 out of 52 again. You put that card still back in the deck. Okay, you still have all 13 hearts still in the deck, so you can still choose it out of 52. Those are all independent events because you're putting it back and you're shuffling it, and so you have another random independent event, right? And so the chance that there will be all three hearts when you keep putting it back in the deck is what we're going to be finding out. Multiply that up. Yeah, 0.015625. So just say it's 1.56%. So pretty small, right? It's a pretty small chance, but there's a chance. You get three hearts in a row when you put it back. But when you do not put it back is when you find different results. I'll do blue. So the first time, right, you have a 1 of 52 chance. Now you're putting it to the side, right? Maybe you chose the ace of hearts. That's out of the deck. Now you only have 51 cards left, and you have one less heart in your mix, but you want to choose a heart. So how many do you have left? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? That's what you want. And we're going to do the same thing. Maybe you pick the 2 for the last one. So now you only have 11 of them, and they're, not 52. That's silly. Let's see if I can erase that. Do one more. Yeah, 52. You have 50. Exactly. Oh. Didn't work. 50. Now you multiply this because it's not replacing it. I got 1.29%. And it should be smaller, right? Because you're decreasing your favorable outcome there. Let's bring them up. Alrighty. Yes, I know these are long examples and I'm talking a lot, but it is important. We're getting down to the final couple pages here. Conditional probability that an event will occur given that another event has already occurred. Okay. So let's see. What we're going to be doing is almost reversing the... Oh no, we're not quite there yet. Never mind. I'll get there when we get to the last couple examples. So use the table to find the conditional probability, equality, control expector. Checks for defective parts. The table shows the results of the inspector's work. Alrighty. Find the probability that a defective part passes. So we're only looking at the defective part category. Right up here. It's either it passed 3 times or it failed 36. Wow, that's a large portion of passing. But the total amount of defective parts when they checked them, right? They checked a total of 39 total defective parts. 3 of them passed, 36 failed. Was the probability that the defective part passed? Well, it was 3 of 39, right? Because we're only looking at the defective category here. Okay, that's it. 7.69% of it passing. And then we're going to do the same thing with this next one. Find the probability that a non-defective part fails. Right, so only looking at the non-defective part, So there's a total of 161 total non-defective parts they checked. Okay, and 11 of them failed out of the 461 of them. And so obviously, like, companies want to make the non-defective ones, lower, and the defective ones higher, right? Probabilities. Cool. It's 18.75%. That will fail. Yeah, you don't want this number to be very high. You want the non-defective things to work. So they want that to be pretty low. Okay. These are the ones that will be a little more interesting, and you really do have to look at the wording. At a school of 60%, 60% of students buy a school lunch. All right. 10% of the students buy lunch and dessert. That "and" is the biggest part of the entire problem. What is the probability that a student who buys lunch also buys dessert? Okay, so here's our formula again. P and probability of A and B equals the probability of A times the probability of B given A. Notice, where's that "and" in our problem? Here. That's what they give us on that side of the equation. So your 10% doesn't go on the right side. It goes on this left side, 0.1 here. And they give you the probability of A, 6% of students buy lunch. They want to know what is the probability of students who buy lunch also buy dessert. Probability that they buy dessert given that they buy lunch. That's what we're finding. This. So if you're going to go back to algebra, right, you have to divide both sides by 0.6. Get your answer. 1/6 is the probability of B given A. Probability that they're going to buy dessert given they bought lunch. That's what that means, right? So 1/6, that's about, oh wow, I messed up on the other one. Sorry, I'll go back. 16.7%. That's what that should be. Sorry, some people are like, what? Hey, you messed up on the last one. Sorry, I just realized that. That's so big. Oh my gosh. It should be 2.39. All right. Hopefully I settled down the people screaming at the computer screen. Why didn't I get that on my calculator? Sorry about that. But yeah, back to this. 16.7% chance that the people that buy lunch also buy dessert. Nice. All right, last problem. We got it out of the 40-minute video. Coffee shop, 80% of, so it's going to be the same thing. Honestly, the coffee shop, 80% of student, 80% of customers order coffee. Only 15% of customers order coffee and a bagel. What is the probability that a customer who orders coffee also orders a bagel? Notice they use the same verbiage here, right? Also, right? It's the same problem. So you have point, and if you want to jump to that answer, that's totally fine. Because you did 0.15 divided by 0.8, right? Or 15 divided by 80. That's another way you could have done it. Equals the probability of B given A, right? And if you wanted to kind of put this again in another way, over here you have the probability of A and B divided by the probability of A equals probability of B given A. Nice. All right, here we go. This is the 18.75%. I was looking ahead in my notes. Apologize. That's probability that the customer orders both coffee and a bagel. Awesome. I think that's the end of our notes. Shoot me a message in case you're confused on something. A lot of these are situational. Each problem is a little bit different. Really read, underline, highlight, context, and I think you'll be good to go. All right.